Hello friends, welcome back to our channel. So in the previous session we have seen the deletion operation in binary search tree. So that means how to delete an element from the binary search tree. So in this session we will go with another operation, that is searching operation. Searching in binary search tree. So in the introduction we have discussed that binary search tree is a combination of binary tree and a binary search. So the searching is very easy in binary search tree, and which is very similar to our binary search. So in that binary search we will find the middle element, and based upon the middle element we are dividing the problem space. So if the key value is less than the middle element, then the search space is reduced so that we are searching the element in between 0 and mid -1. And if the search element is greater than the middle value, then we are reducing the search space and we are only searching in mid +1 to end element. So based upon the middle element we are reducing the search space in the binary search. So here the middle element is nothing but our root node. So coming to the property of binary tree, binary search tree, so all the elements of left subtree should be less than the root node, and all the elements of right subtree should be greater than the root node. So here in our searching process, this root node is a middle element, right? So based upon the root node we'll go with the searching, right? So if the key value is less than the middle element, that means if the key value is less than the root, then the search space will be on left subtree, and if the key value is greater than root, the search space will be on right subtree. So here the three steps. So first one, key is equal to root, automatically we will find the element. Second, key is less than root, so here the search space will be reduced. So search space will be in left subtree, right? So according to our BST property. The third case, key is greater than root. We know that all the elements of greater than root will be on right subtree, so the search space will be on right subtree. So this is implemented in a recursive way. Okay. So here see, for this, if it satisfies key is equal to root, then we have to return, search is successful, right? So search is successful, that means element is found in the binary search tree. And if key is less than root, we have to again call the same process, but now the search space will be in the left subtree, right? So again we have to follow the same process. So recursive call, all these are implemented using a recursion. By recursively we can apply this searching technique, right? So let us take an example and then we will see the logic. So very simple, only three conditions: is equal to, greater than, and less than. If all these three conditions fails, that implies The element is not found in binary search tree. See, let us take a few elements. Example, let us take 50, 30, 70, 20, 40, 60 and 80. So these elements, first let us construct the binary search tree. So 50 is a root node, 30 is less than 50, so on the left hand side, 70 is greater than 50, so it's on right hand side, 20 is less than, so left hand side, and 20 is again less than 30, so left hand side, 40 which is greater than 30 and less than 50, 60 which is less than, greater than 50 and less than 70, 80 which is greater than 50 and greater than 70. Right? So this is the binary search tree for the given example. So we'll first represent this binary search tree in the list format. So list format, if you consider the list format, so we know that three fields will be there. The first one is data, the left hand side is the address of the next left subtree. Right hand side right again. Right. See, so this is 50, 30, 70, 20, 40, 60 and 80. Right. So this the address of this one is, let it be 1000. I will write here. So the address of this one is 1000. This is a 2000. This is the 3000. The address of this one is a 4000, 5000, 6000 and 7000. Let us assume that. So 50 left hand side, it address the 30. So what is the address of 30? 2000. So here we have to write it 2000. Here it is a 3000. So we have seen the representation of a tree, right? So here it will be the 4000, then 5000, 6000 and 7000. So here all these are the leaf nodes, right? All these are the leaf nodes. So all these are the leaf nodes, so it will be null. So all these are null because it doesn't points to any other element. Right. So all these are null. Now we have to search for an element. For search an element, we need a key value. So let it be a key is equal to some 40. Key is equal to 40. Right. So first coming to the root node. So we have to check the three conditions. Is equal to root, less than root and greater than root. So 40 is equal to 50. False. Now compare 40 and 50. So 40 is less than 50. So the 40 can be available on left subtree because all the elements which are less than root will be available in left subtree. So now we have to go with the left subtree. We have to reduce the search space to the left subtree. Again follow the same procedure. In the left subtree, what is the root? 30. Again key is compared with the 30. So 40 is equal to 30. False. So again compare. 40 is greater than 30. So all the elements which are greater than 30 will be available on its right subtree. So again the problem space is reduced to right subtree. So first left subtree, then right subtree. Again follow the same process. So key is equal to 40. Here the right subtree root is 40. Only one element is there. Fine. So automatically this 40 address will be returned. So here we are returning the address of the position. So just start node start search So here we are taking two parameters, one is a root and another one is a key. Now here we can write the first condition, if root is equal to null, simply we need not go for the process, so just return a root, right? Else if the key value is equal to root of data, that implies the search element, the key element is found in the search tree. So we can simply return the root. Else if key value is less than root of data, we know that all the elements which are less than the key will be available in the left subtree. So we have to call recursively return search, again the call the same thing, search. Now the element will be root of left comma key, right? So hope you understood. First we are writing the root and key, two parameters. In the recursive call we are reducing the problem space or search space, so that root of left comma key. Else, so if both the conditions are failed, automatically we know that the key is greater than the root of data. So else we can return search of root of right comma key, right? Hope you understood this statement. So only three cases can be done for comparison of two variables. One is it may be equal, another one it may be less than, or another one it may be a greater than. So if these two condition fails, automatically it will the key value is greater than root of data. So if the key value is greater than root of data, we know that all the elements which are greater than root will be available on the right subtree. So we are simply writing here. So this is a code. So let us test once. So key is equal to 40. For let us take key is equal to 40. So key is equal to 40. First start node root. So here the root means the 1000 comma 40 will be passed as a parameters. So 1000 is the root. Now root is equal to null. So 1000 is equal to null. So that is false. 1000 is equal to null is a false. So else if key, so 40 is equal to root of data, so 50. It is also false. Now 40 is less than 50, true. 40 is less than 50, true. Now search root of left. What is the root of left? Root of left is 2000. So this is a 2000, this is a left and this is the right. So return search root of left, that means a 2000 comma 40. Now the search space is limited to this left subtree, right? So just remove this. So after the first recursion, in the next recursion, the element are, the address is 2000 and the key value is a 40. Now again we have to proceed with the same process. So here 2000 is equal to null, false, right? So 40 is equal to 30, false. So 40 less than 30, false. So if all these condition fails, automatically search. So 40 is greater than 30 automatically. So root of right and key. Next iteration or next recursion, we have to go with the root of right and key. Here root is 30, root of right is 5000. So 5000 comma 40. Right? So in the second recursion, right? So here 5000 comma 40. Again repeat the same process. So 5000 is equal to null. 5000 is equal to null, false. So key 40 is equal to root of data, means root here 5000. 5000 of data is 40. So 40, true. So it returns the root. What is the root? 5000. So it will return 5000. So that means our element 40 is available at the position of 5000, at the address of 5000. Right? So hope you understood this example. Let us take one more example. That means we will change the key element which is not available in our binary search tree. Let us take a 10. Let us take 10. So we know that 10 is not available in our binary search tree. Now we will trace it. Right. So let us trace this one. First 10, key is equal to 10. So the root is obviously 1010. So 1000 is equal to null, false. So 10 is equal to 50 because root of data is 50, false. So 10 less than 50, true. 10 less than 50 is true. So search root of left means 2010. So now in the second recursion it will be 2010. So now repeat the same process. Repeat the same process. So 2000 is equal to null, false. So 10 is equal to 2000 of data. What is the 2000 of data? 30. False. Next 10 less than 30. True. So again the problem space is reduced. The search space is reduced to left of root. So what is the left of root? So root of left. Here what is the root? Root is 2000. 2000 of left is a 4000. So 4000 comma 10. So in the next recursion the address is 4000 comma 10. So here 4010. So again the same process. 4000 is equal to null, false. 10 is equal to 4000 data. Excuse me. So 4000 of data means 20. So again it is a false. So 10 is less than 20. True. So again reduce the space. So root of left, here root is 4000. 4000 of left is a null because it is a leaf node. So it is a null, comma, key is 10. Right? So again recursive call, repeat the same. Here it is a null. Now null is equal to null. True. So automatically it will return the root. What is the root? It's nothing but a null. So if it returns null, it implies the data is not available in our binary search tree. So this is how we can apply the searching process in binary search tree. So just for understanding, I have represented this binary search tree in a linked list representation, double linked list. Right? So hope you understood this one. Let us stop here, and if you are having any doubts regarding the searching procedures, so this searching procedure is similar to our binary search algorithm. So there also we are checking the three conditions, whether is equal to, less than, or greater than, and recursively we are finding the middle element. So here also recursively we are finding the root element, and based upon the root we are checking the conditions. That's it. Right? Okay. So let us stop here. If you are having any doubts regarding this searching process,
Feel free to post your doubts in the comment section so that I will definitely try to clarify all your doubts. And if you really understood my sessions, like my sessions, share my sessions, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.